Hi, this is Dr. Doobie again, coming to you from a particularly rainy Alabama afternoon. I'd like to chat with you today about a non-ideal topic, and that would be non-ideal solutions. How do we model the VLE behavior? I've told you about using polynomial equations, but how about a more rigorous method, such as an activity coefficient model, like the Wilson equation? Let's talk about that a little bit. Here is the vapor-liquid equilibrium, in particular the XY diagram, for THF and water at 1 atmosphere. THF is tetrahydrofuran, a very common solvent. And this data comes from the Dortmund data bank using, they are citing this article that came from 1968 in the Journal of Applied Chemistry, USSR. Interesting, that doesn't exist anymore. Now, all these are data points, and you can see this is highly non-ideal and is not at all described by Raoult's law. In fact, it's an azeotrope. It crosses the 45-degree line here, and the light component reverses roles. It's THF here, and it's water up here. If you're distilling from these concentrations here, you can't get past this point, this azeotrope, with just simple distillation. There's a whole books written on azeotropic distillation that I won't get into, and I didn't actually get into that in my book. Maybe next edition, a little bit. How to get beyond these azeotropic pinch points. But for now, let's just decide how we're going to model this data. And there's several activity coefficient models that we could use. In particular for azeotropic systems, the Wilson equation and the Uniquac model can work pretty well. These fits of the model are done by the process simulator ChemCAD. In one simulation, I asked it to use the Uniquac, which is this orange line, and in the other simulation, I asked it to use the Wilson equation, which is the blue line. And you can see here that both do a pretty good job up here on this side of the azeotrope. And they both predict this very large increase in y with x at small x values. But the Uniquac model seems to kind of overshoot here and then come down, which the data does not do. The Wilson equation, it's not perfect, but it does a pretty good job. It's a little bit below the data here, a little bit above the data here. It looks like it crosses the azeotrope at a little bit higher point than the data or the Uniquac model. And then they both do a pretty good job up here. Well, how do you come up with what is the Wilson equation? How do you come up with the constants that would describe this data? And what is very miraculous almost is that we can use just this azeotropic data point to come up with the constants in the Wilson equation, which I will show you, to model the entire range of VLE data. You might be thinking, wait, really? You can get a model that describes all of the VLE behavior with just the azeotropic data? Well, you can. Let's look at Raoult's law, the modified Raoult's law, that says the mole fraction in the vapor phase times the total pressure is equal to the mole fraction in the liquid phase times the vapor pressure. That's Raoult's law. And then we multiply this by an activity coefficient that captures the non-ideality of a solution. If it's an ideal solution, gamma, the activity coefficient is simply 1. Now we know that at the azeotrope, the value in the vapor phase, the composition is the same as in the liquid phase. So we can rewrite that equation as gamma is equal to the total pressure over the vapor pressure. So if we know the composition and the temperature of the azeotrope, we can calculate the activity coefficients. Now here I've written out the Wilson equation for you. You can come back here later to write it down, or you can just get it out of the book. But anyway, it says that the log of the activity coefficient, that's a natural log, of chemical 1, and this is written for chemical 1 and 2, that would be your THF and water, is equal to minus the log of the composition of chemical 1, the mole fraction, plus this lambda 1, 2 constant. And that's just the way the constant's usually written, times x2. And then plus x2 times another function, which is written down here, which I just put as a phi here because it's common to both equations, as we'll see. And that just simplifies the writing and reduces the chances that I'll make an error in my inputting of this equation to a spreadsheet. And here, for the other chemical, we have log of gamma 2 is equal to minus the log of lambda 2,1, a different constant, times x1 plus x2, minus, this is different than up here, see this is minus, that's plus, x1 times phi. And I may be the only one that writes it this way, by the way, but it's just to simplify the equation. Then this phi is this term that's common to both equations, lambda 1, 2 over x1 plus lambda 1, 2 times x2 minus lambda 2, 1 over lambda 2, 1 times x1 plus x2. That's the Wilson equation. Now at the azeotrope, we know the activity coefficients, we know the compositions. And down here in the second equation, we know these compositions. Actually, x2 is just 1 minus x1, right? For a two-component system. And for this phi term here, we know these compositions. And what does that leave us here? We have two equations and two unknowns. We can use solver to iterate for these two constants. And then we can use them over the entire range of compositions if the Wilson equation does a good job of modeling the actual VLE behavior. Well, we'll see. Here is a section of the spreadsheet which I'll call Azeotrope, and it'll accompany the tutorial so you can look at it, where I determine the value of the constants lambda 1, 2 and lambda 2, 1. The azeotrope is about 0.82 mole fraction THF and therefore 0.18 mole fraction water. And the temperature at that point was 63.5 degrees C. Now, I have seen slightly different values for these compositions and temperature in other resources, but I'm just using the data that was in the Dortmund set. Now, the vapor pressure of THF and water is just calculated using Antoine's equation and this temperature. And then you saw how we can calculate the activity coefficients as just the total pressure over the vapor pressure. Now over here, I have the Wilson equation inputted here with all terms on one side so that when it's satisfied, it should be 0. And up here, I have just numbers in here for the constants, the lambda constants. F here is just that phi common term that I have written here. So what I did is I put 0.5 in here originally, And then I asked Solver to change those until the Wilson equations both equaled 0. And these are the values it came up with. So these are my values that I came up with for the Wilson coefficients. Now, of course, that will depend on how these were iterated, and it'll also depend on what exact values you used for the azeotrope. Now, here is how I generated the XY data for THF and water in the spreadsheet. And I just shown the first few steps here. So here's the THF mole fraction. Then the water mole fraction is just 1 minus that. And this will be a guessed temperature. So I basically went between the boiling points of water and THF. Then I calculate, based on that guessed temperature, I calculate the vapor pressure of THF and water. And then I calculate that common term that I called phi. Here I just put an F there. This is based on the lambda values that I calculated, and then also these compositions. And then from that, I use the Wilson equation to calculate the gamma, the activity coefficients. Now, over here, I use the bubble point equation to iterate for the correct temperature for these compositions. So remember, the bubble point equation gives you the equilibrium temperature for liquid phase compositions. So once these have been correctly determined, then I can use the modified Raoult's law to find the Y value for the corresponding X values. So that's how that spreadsheet generates the VLE behavior. So here is that data again with the two ChemCAD fits of the data. And then the blue line is my fit. And I actually like it better. I think it did a better job of matching the data in this region, and pretty much the same as the Wilson equation in ChemCAD. Maybe right up in here, ChemCAD followed the data a little bit better, but here is where we would be doing most of our distillation up to the point of azeotrope. We can get an even better comparison of how the models represent the VLE data by expanding the y-axis. Here you see it goes from 0.7 to 0.9. So we get more of a close-up of this azeotropic region, which occurs about 0.82. And of course, the Uniquac did not do such a good job. The Wilson equation with my parameter, I think, still did a little bit better job of matching the data, but the ChemCAD equation did almost as well. You might notice that I called this Doobie and then the Wilson equation. That's fun for me because my stage name is Doobie Doghouse Wilson when I play in all those low-life dives around here. It's a little tricky using the Wilson equation for VLE behavior in a simulation, and I will be showing you how to do this in another tutorial.